able to skip some of those ones at the end. So we'll figure that out right now. Here we go, number 2 and number 8. Now I know you don't have to memorize this one. You didn't even have to do homework problems on this one. But technically, I was curious if you would go look and find a Precalc sign for the lower and upper bound. But yes, you don't have to memorize. I'm going to show you in the notes what they are. Again, I think I popped it up on the screen for 2 seconds at the end of the video. But you didn't have to do those problems at the end with Precalc signs or lower upper. Number 2, linear factorization theorem. Number 26, you were listing out the possible zeros from our rational root test, or our rational zero test, the fraction where we take the factors of that guy over the factors of that guy, and then we pair them all up. They found that 3 works. And so from that, guys, I know the book shows it weird, but what is this? Yeah, it's just synthetic division. Synthetic division, right? Whatever, you do the box, they do, okay, whatever. But synthetic division, it went in evenly, so we knew x minus 3 was one factor. We could write the quadratic, and then we break down the quadratic. Whoa, that was magic. No, they just don't show their work. Or they do guess and check like I do. How would you guys have done this, guy? You had to factor them, right? Yeah. Positive 9 and negative 10, right? Which would have been negative 9 and negative. And then he would have gone ahead and written over that. Daniel, stay on top of me after class. I had no idea where you were. Write a 3 on top of each of those. I would reduce a 1 and a 3. So I have x minus 3 and 3x minus 1. Dun, 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 boom, boom, boom. Oh, only 2 zeros. Because isn't that a 3 and that a 3? They're both the same 0. Multiplicity of 2 if you want to be super snazzy. Ooh. Unless it's not going to work, that's fine. And then this one is a positive 1/3. How big is it? Huh? Oh, did you plug them all in and figured out all 3 of these are zeros? That works, but most people wouldn't like plugging 1/3 into that. Hold on, pause. Steve brought up a really good point. You guys ready? She said that she just started plugging in all of these, and she found the ones that worked. 3 worked, and 1/3 worked, and all the rest failed. So she was like, sweet, 3 1/3 done. What's the problem if you're taking your test where I already told you cannot use your calculator? Plugging 1/3 in. 1/3 squared is 1/9. 19/9. Who wants to really do that? Now, I'm not saying you can't. I'm just saying, remember, just because you have your calculator at home with homework doesn't necessarily mean that's going to help you on the test. I already said no calculator. I'm sorry, it's true. Because you could graph and find the zeros and just kind of dodge every single factoring problem. So, just a warning for the majority. Done. But, heads up, you can always find the rational zeros by plugging every single one in and find the zeros. That's true. 30. Please tell me you took out the GCF. You had tons of different possible zeros, but who's starting at 12? Come on, we all start at 1, right? Yeah. Negative 1 should have showed up pretty quickly. We have a quadratic, we factor and we're done. Oh, did you remember the 0 in front? No. I remember all your factors. Just because you pull one out doesn't mean he leaves. He's still there and he has to have a 0 too. Number 38. You guys realize number 38 was actually a really easy one? No? No? None of you? Why am I making a modified x method for a 4th degree polynomial? That doesn't make any sense. It's a trinomial. Check it. I know it's weird because it has x to the 4th and x squared, but it's a oh my goodness. Crazy. It's a trinomial. Since it's a trinomial, we could just do a modified x method. So I went ahead and got my 16, my negative 17. Now, here's where the modified x method, Nikki, I see it. I'm guessing it's this problem, right? Yeah. Give me a sec because we're down here now. Are we okay with negative 16 and negative 1? Yes. Are we okay with my putting of a 4 and a 4? Mm-hmm. But here's the struggle. When we, I'm not going to do x minus 4 and 4x minus 1. These aren't x terms. Why are they x squared?
Because it's x to the fourth, not
it's
x
to the
squared.
fourth, not x squared. So when I go to do this, it'd be x squared minus 4 and 4x squared minus 1. See it?
Wait.
Nathan sees it. Did the rest of you see it? Technically, wait a minute. Well, what's the whole point of this? Like, what are we supposed to be? Oh, I was just showing you his factoring would have been easy, and then we could have gotten, couldn't we have gotten plus or minus 2 pretty quickly? And couldn't we have gotten plus or minus 1/2? Add the 1, divide the 4, x squared is equal to 1/4 square root. We could have gotten them pretty quickly with factoring, but yes, your calculator works too. Nikki, you've been so patient. What's up, kid?
So if the I understand now.
Yeah.
From the beginning, I was wondering why we could get all. I could use the rational theorem thing if the last thing.
Oh,
yeah.
because you're looking here, you didn't finish the at first. Okay, my alligator people, stop communicating. All right, so number 68. Did you guys find the imaginary zeros okay? Because that was just square root of a negative number. If you guys look at the work off to the side, which brought in the 4i.
Oh, no.
The difference of squares, no? A squared minus b squared, but a squared is a y squared, and b squared is 16. And then that's a nice, oh, a squared minus b squared, haha. And then, nothing. Wait, imaginary number or something. And then what's super cool about number 96 and why I'm not even going to talk about it? Didn't have to do it. What else did she have to do? 96 or 80?
80 something.
89.
I crossed it out very violently.
Alright, 89 and 96 you did not have to do, but the other ones you guys were reading off, those were not, yeah. This is the ones that, these are the ones you didn't want to do. Doesn't mean you didn't have to do. What was going on in that one? Oh, you're allowed to use like a graphing utility to figure out which ones were right? Okay. Those are some fun. And then over here is where it got really weird as far as, okay, as soon as you saw that, stop. As soon as you saw that, stop. Good. Guys, looking at homework. Looking at homework, the notes that we took yesterday, and it's on this page, would have helped you with which problems? Where were the really crazy problems? Yesterday, the ones that I did in class on the video last year, and you guys were able to see, all came from this section because they were trying to tell you, hey, here, we'll tell you one. But then as soon as they tell you one imaginary, what do you know from yesterday?
2.
Okay, complex zeros always come in pairs.
And negative, because they come in pairs.
Why do they always come in pairs? But where are they coming from?
They always come in pairs.
Conjugate.
Because the A plus B plus minus and I don't know.
Where are the imaginary ones coming from?
That.
And what's right before that?
Plus or
Plus
minus.
or minus.
2 answers once you know one. No. So all of these are really just simplified. X equals negative B plus 2 minus 1. Oh. These are quadratic formula answers. Now yesterday I didn't have you guys like work backwards from the quadratic formula. Look, we're missing like 3 different variables. No. Instead we said, sweet, if we know 1, we know 2. And if we know 2, what did I show you yesterday? For instance, which one did you guys do?
57.
7? If you knew 5i, let me erase this real fast. Oh, it actually does work. Oh, it does. That's kind of cool. Sorry. Learn something new every day.
What is happening?
What?
Yeah. If you know one, you know both, right? Plus or minus for the 5i for the one you needed to do. Couldn't we make that into x minus 5i times x plus 5i? Isn't that what I did yesterday?
Yeah.
Take the zeros, make them into factors. From the factors, couldn't we do a difference of squares and say x squared minus 25i squared, which isn't I squared a negative 1? And as soon as we, this leads me to that going into this. How do we figure out who's left? That's not different. Well, it's a difference of complex squares, but that's complicated. We already knew that. They told us that. We know these guys. How do we use this to break him down all the way? I heard division, but which one? What's the only legal? Log division. So that's what you guys did in notes yesterday, theoretically, is you saw some nasty examples. I don't think I have last year's notes copied into your notes yet. So the work isn't shown, but that's what you guys did yesterday. You didn't have to do that one. You were given something nasty like, it's a factor. What are all the rest? But then even before that, we did an easier one, didn't we? Yesterday? Where it wasn't like the plus or minus, it was just a little baby 3i, and if we know a positive 3i, then we also know a negative 3i. So pretty quickly yesterday, hopefully I made the factors. And then I multiplied my difference of squares, and eventually we would have gotten x squared plus 9, and then that one's x squared plus 2x plus 1. And then we multiplied, what were we trying to do? Oh, we were just finding a polynomial, but they gave us the stuff we needed. We just had to actually find the polynomial. And then didn't you guys have to think about distribution, right? And you would have gotten to your final 4th degree polynomial with me yesterday. That one wasn't too bad because you were able to foil that really quickly, really easy. What was the one you probably really didn't like? That one. Because what was nasty with it? Yeah. And that's exactly like in homework. Which one did you do? Did you have one of those nasty ones, or did I say you? Anything from 58, 59, 60, 61, 62? Oh, spoiled rotten. So we did a really nasty one yesterday, and then I didn't make you do it for homework? You're welcome. Anyway, from the video yesterday, you saw how nasty it. Ooh, Algebra 1, we're learning foiling. See little sand things? Anyway, you guys didn't learn foiling that way? Yeah, you would have done this. Oh no, you would have had to do. Oh, yesterday was, yeah, it was a little weird because you had to do minus 1 plus 3i and x minus 1 minus 3i. And then you had to foil. Hey, we could do a smiley face, okay? So we could do first, outer, inner, left. Anyway, you saw me do the example yesterday, minus the smiley face I'm teaching in Algebra 1, and it was nasty, it was mean, but it's not what was in homework. This whole page, why am I about to delete it?
Oh, because it's discard trash.
I wouldn't say it's trash.
Because it's discard's rule of science.
It's not wrong.
It's incorrect.
Okay, my computer's frozen.
Oh.
What are all the possible factors for 60? And then for 3 or for 1 to 1.
Here's my question, guys.
Oh, so this is just for that. Yes.
Thank you for enjoying each other's company.
And then
I can unlock away. You guys just start fellowshipping. But now it's time to stop fellowshipping. Okay. point out why the book is giving you a hint on this polynomial. And you should be able to figure it out yourself. Let's try. Why is the book giving you a hint on this polynomial? Where would you start? If I just gave you this, absolutely no hint, and said, go find the zeros. What's wrong with him?
He's not part of the group.
No, he is. There's just a lot of factors.
Exactly, because 1 goes in, 2 goes in, 3 goes in, 4 goes in, 5 goes in, 6 goes in, and then we have to have all their pairs. Wait, 10 goes in. We have to have all their pairs. And then we start doing, 10 and 6, 5 and 12, 4 and all those get doubled. And all those get divided by, you're lucky, just 1. What if that was a 2 or a 3 or a 4 or a 10 or a 12? Do you realize the possible, Sid just said a second ago, she tried all of those zeros and found the ones that worked. How many would she have to test this with?
A lot.
Without dividing one that works and breaking it down, it's nasty. So they gave you a hint and said, hey, all right, 2 of them are imaginary. Wait, if 2 are imaginary, how many are real? 2 of them. So either they're 2 real nasty zeros from the quadratic formula, in which case none of these would work. Or 2 of them are nice zeros, we have to look at them in a list of like 20 different values.
24.
So, why would Descartes' rule of sign and the lower and upper bound rules be helpful? These can get nasty, and if there are tricks to narrow down where you look, you can ignore this whole set of zeros that aren't even going to matter. Descartes' rule of signs, if you do a synthetic division on this problem with a 4, even though 4 doesn't go in, if you did synthetic division with a 4 and it was a positive, 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 Descartes' rule of signs would say, forget it, you're not going to find any more, any higher. That's kind of snazzy if you have a nasty long list. So let's think. How am I going to test you on this? On a test day, you hope there to be at least like 20, 25 different problems, and not every problem is worth like 10% of your grade, right? You want lots of problems on a test. If I give you lots of problems on a test, can I give you a nasty one with tons of factors? Yes. If I was to give you like a 3-problem test, yeah. But am I going to do that as a high school teacher? Probably not. So why am I taking out Descartes' rule of signs in the lower and upper bound rules? Because I'm not going to give you one so nasty that you really need those rules to help you out. Does that make sense? Yeah. I'm going to give you ones with like a 12 or maybe like an 8 or maybe like a 6 so that you only have a few to test. Now, plugging in, it's great, but it can get nasty. Ultimately, you want to go to synthetic division once you find one that works, right? That's the big moral of the story for section 2.5. Could it have gotten worse? Yes. Was this bad? Yes, but I didn't give you any homework on the worst type. And I'm throwing out those little hints and tricks for narrowing down huge lists of possible zeros because I won't give you one near this extensive. Does that make sense? My 3 people that agree. Thanks.
Is the rule applicable to all Chinese countries records?
So it is kind of cool because if you had like a huge nasty long, it literally would say, just stop looking, go back to this one. Like it is a helpful rule, but I'm not going to give you one that long. That's why I don't want you to stress about memorizing it and trying to practice it and us taking more classes. Guys, I think we've graded all the evens that you needed to do, right?
Yeah.
Is there anything that, in the ones that you needed to do, you guys still got stuck on? I know I didn't give you the nasty 1 plus 3i or the rules. Is there anything else you got stuck on in there? Oh yeah, thanks. It was 15, right? Yeah. Cool. Sorry, computer's frozen. It's okay. Any other questions you guys want to ask? Emma.
Break down number 30 and still a little bit.
33, yeah.
Yeah.
Anything else besides number 30? Is that 5 of seven? Yeah. 51? 51 and 60. Anything else? Okay, let's see if... Oh, hey, it changed. That means it's happy again. Here we go. Oh, wait, Emma, you did have to do 60?
Oh, 30.
Oh, 30. 30 was the one that came first, and then we'll do number 51. So number 30 Nikki, this is the one that you didn't like. So help me out. How should you have started?
Take out the x.
Perfect. So if we take out the x, we have a cubic polynomial that actually has a constant last term for us to go look at all of our possible zeros. The way that we've done it in class is make a big old fraction, factors of the first over factors of the, factors of the last over factors of the first. Say 1, 2, 3, 4.
Is that plus or minus?
Plus or minus. So Emma, in the directions, it didn't give us anything besides just find all the real solutions, right?
Mm-hmm.
So with that, okay, we know we don't have to look into the imaginaries, but we still have to find all the reals. Well, let's start with the nice ones, because the nasty ones, I hope we could get to a quadratic and do the quadratic formula. I'm lazy. I start with 1. Anybody else get to that in section 2.5? You just started with the babyest number and the easiest, right? And so if we plug in 1, we could plug it in here, or we could plug it in here. I'm just going to be lazy and plug it in the one with the fewer powers. So 1 minus 13, negative 12 minus 12, I'm in trouble. But didn't you notice 12 and 12? So negative 12, bad idea. But if I have a negative 1, that would be a negative 1 plus 13 minus 12. I'm pretty sure he's going to be just great. So I'm going to take just that guy because I already know the x. I'm going to break him down. So I have a 1x cubed, a 0x squared, a negative 13x, and a negative 12. That's my remainder box. We're good on synthetic, yeah? Remember what synthetic does. It says, hey, you knew 1 solution. So right now I have x equals 0 from the front dude. I have negative 1 just from plugging in. And you can find whatever you left. But to do that, I need to look at this guy right here. So far I have an x. I have an x plus 1, if that's the 0. And now I have an x squared minus x. I'm just going to think factoring, figure out who that guy gets me. And pretty quickly. But be careful. These are the factors.
Wait, isn't it switched?
Isn't it negative 1?
Yeah, but isn't it positive 1?
Pause. No. It is x minus 4 and x plus 3, but check it. We have to find the zeros of those. And so the zeros would say add the 4, right? Mm-hmm. And then subtract. Because your factoring method, it doesn't get you the zeros, it gets you the actual factors.
Got it. Okay.
But I know you've been thinking like single numbers are, you have to remember factoring came before all that. Okay, cool. And 51, true? 51 was here at the bottom. Was he the one with the really weird directions? Yeah. Wait, you were supposed to do 51, weren't you? I wanted you to. Okay. Okay. Out of the entire homework, this problem made you understand the math the most. You guys see all the terms in there? Yeah. Like, holy cow, you have polynomial, product, factors, irreducible, rational, product, linear, quadratic, irreducible, reals, and, well, if this is reals, what do you think this one is if it's more? What's more than reals?
Imaginary.
Imaginary or complex. So basically, ready? These ones say keep it nice. That's letter A. Letter B says keep it real. Letter A says keep it nice. Letter B says keep it real. And letter C says all of them. Means you can go imaginary. But what's the really, 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 really nice thing about number 51 that I gave you?
It's a trinomial.
It's a trinomial. Which means? No! I went trying all the different factors in 20. Well, okay, that's not too bad. 1 and 3 and 9 and 27, right? Mm-hmm. But still, plus or minus. Would have been a lot easier to be like, oh wait, it's a trinomial with a fourth and a squared and a. I could just be looking for x squared terms and member terms because I can have an x squared plus minus and an x squared plus minus. to make my trinomial. Now guys, check it. Could you have done the same thing if that had been like this?
No.
No. Because I need this to be something squared plus the square root. I can do that with this one. X squared times x squared, and then just an x squared, and then a number. I can do that here, but I can't do it there. This one is not a modified x method. This one is. Oh, well, I think 9 and 3, yeah? Which, good. Check it. We don't have anything to do our whatever with, so we can just go ahead and think of
X squared.
stealing the 9 and the negative 3. But Nikki, you gotta think of who's the actual guy in the quadratic. X squared. If it was t squared plus 6t minus 27, I'd put t's there. But since it's x squared being squared plus 6 times x squared, t's the guy that goes there. Now, why am I going to stop for letter A that says keep it nice? Why not keep going? Well, that's imaginary, but that's letter C. What's letter B going to do? Why is he not nice?
Oh, because there's a negative. Right?
Well, but we don't mind negatives. Those are differences of squares, but what's the square root of 3? He's not rational. Remember how we had the reals and the imaginaries, and the reals had the rationals and the irrationals? This one said keep it nice. A 3 and a 9. Stop. This one says, okay, fine. The reals can get nasty. Okay. But still, keep it real. Okay, fine. As far as the coefficients. And then, Kimia, now it's your turn. Because you said, what's this one going to give us? Yeah. And if you square root a negative 9, remember we have set this equal to 0. Subtract the 9 plus or minus square root. That's where we go getting r. So whenever earlier, even I said you cannot factor this, was I right? You can factor it. Yeah. But what are your factors? They're not real, they're imaginary. So until we covered complex numbers, could we factor it? No, not in context of this class. From algebra 2, I guess you could have factored, but how many of you think of factoring this to be i's? If you're trying to factor that, you're like, ooh, x plus 3 times x plus 3, you're killing cookies. So sad. You can factor an addition of squares, but they're not. 51 people, I forgot who you were. I'm so sorry. Did I answer your question? Okay. Section 2.6, you already started taking notes. Oh, that's not you. Yes, it is. Here it is. Speaking of rational numbers, let's go to rational functions. Came in handy in calculus. Speaking of rational, actually no, it says I'm doing rational numbers. It does. Ratio fraction. You have fractions of functions. Now you have fractions in functions. You have fractions with functions, aka the numerator is a function and the denominator is a function. Rational functions, you have fractions with functions. Maybe a better way of saying it is not even just with, maybe it's fractions of functions. Whenever we say of in math, it means something's been plugged in, right? Fractions have tops and bottoms, numerators, denominators. A function has been plugged into the top and plugged into the bottom. And to be honest, to be a rational function, the one that has to be a function is just the denominator. To be honest, I am going to show an f over a g, but guys, look at the very first example. Who's your f? 1 is just a number. So the key is that you have functions in the denominator. Why do I have a domain thing right here? Don't we have a domain problem that a denominator can't be 0? So we have to remember that for our d, we have to find the zeros of the bottom. domain, we have to find the zeros of the bottom, aka factoring. So it starts off super easy with something we would have done in chapter 1. Guys, what's the domain of 1 over x plus 2? P.S. This rational function. What's the domain?
Not anything but 2.
Anything but
Negative 2.
Negative 2. Careful. Anything but negative 2. If you want to be snazzy, you could go ahead and put that in interval notation. It could be snazzy, but I don't mind those. Good. So all of our rational functions, as long as the bottom can be 0, it's not one of those imaginary 0 things, then we're going to have domain restrictions that we have to keep an eye on. You guys wouldn't mind showing yourself a quick note? These will be some of you are going to get confused when you're checking the odds and you see this written at the end of problems. Even if they don't say find the domain, if for any reason one of these rational functions gets rewritten, and it can get rewritten without a denominator, they're going to still put the domain saying, no. If it was written like this at the beginning, this is not allowed to happen. So if the book's writing it, something happened to make the domain problem seem like it was gone. And they said, no, you can't forget. There's a domain problem at the beginning. There needs to be a domain problem at the end. So you're going to see some of this written in answers, and you're like, why is it there? It's there because the domain is saying that's not allowed. And I can show you why they're going to write that with the next example. So over here, you guys are taking notes, so hopefully it's good for me to change the page. This is going to be rewritten as f of, wait a minute. That doesn't have x's in it. What does it have in it? Oh, it shouldn't be f of x. Typo. Change it. Does that make more sense? Does it now make more sense? It's not f of x. It's f of t. But check it. The book would rewrite this as t minus 1 such that t can't be negative 1. That's how they would rewrite it. But whoa. They killed some kittens on that one. I don't know what's going on. Nah, they did totally legal math. What did they do? What context is this given? This guy can be factored.
Minus 1 is also equal to t plus 1 times t minus 1. Factor in t plus 1, but t cannot equal negative 1 because that would make the denominator 0.
Well, we'll figure out who x minus a is in just a second. I just saw the word factored and I said, okay, let's do it. And what happens when we do it? You get a rewritten form where what can happen? Kind of. I'm going to put the technical term. The technical term is you can reduce without killing kittens because what's true top and bottom? A shared factor. If it was 5 over 5, we would reduce. If it's t plus 1 over t plus 1, we're going to reduce. So factored out, what I mean is reduce away the denominator. What's the context? Guys, I'm talking about wholes. Wholes are technically defined to be, or described to be, removable discontinuities. Whoa, Nikki, here you go. Here's your answer. Discontinuity, that's where there's a problem. So there's a problem at A, and where do problems show up in fractions? So normally we have x's, this time we have t's. So this one has x's, don't worry, we're coming. But basically, the x minus a is the problem. The x minus a is the denominator that could be equal to 0. If you have a problem at x equals a, whoever that a is, x minus a is the factor that's going to be chilling down here, messing everything up. So if you look in context of the page before, didn't we have an x minus a, x minus negative 2 that was down there chilling, messing everything up and giving us a domain problem? So he's just basically the denominator. The denominator who has a 0, whose 0 messes up the function somewhere. So, coming back. example. This is general. This is general. Here's our specific example. Our specific example says, what if I was to ask you to graph that? How many of you, if that was the problem on the board, back of your homework file, graph t squared minus 1 all over t plus 1, how many of you guys would have done a graph? Even better yet, who would have done a graph without using a calculator or a table? You just would have gotten it right away. Nobody? Who thinks they can graph it now? Only 2. Oh, it's such a struggle, guys. It's algebra 1. No, it's not. That's not an algebra 1 function. That's wait. If this is this, and this is this, then this is just a
linear. Oh, line. Are there 2 zeros?
Where's your intercept? Negative 1. What's your slope? 1 over 1. No, that's not a line. Yeah, it is. You factored it, you reduced it. It's a line. It's an mx plus b or an mt plus b. It's just a line. Oh, but we have to say something's wrong there, don't we? Negative 1, where will you be on my line? Well, negative 1 minus 1. If I don't look here, negative 1 minus 1 is negative 2. Oh, duh, it's a line. What am I putting at negative 1? This is a line with a hole. And mathematically, how can I know it's a hole? Well, because the denominator was able to factor away the discontinuity. Anytime you can factor away discontinuity, there's a hole at that problem at that place. But the rest of the function's just fine. It's whatever's left when you divide it. Ooh, that was a really important comment. Did you guys catch it? Whenever the denominator can be factored away, the remaining function is just whatever results from the division with a hole. So was that guy a line? Yes. Did I expect you to know that walking in today? No. But do you see it now? Anytime the denominator can be factored away, I have a hole, and I can look at him like the division or like the factored form and like the whole line. Removable discontinuity, that is a hole. But are those the only domain problems that can happen in rational functions? No, there's one more. This one, did negative 1 make the bottom 0? Yes. Question, is negative 2 going to make this bottom 0? Yes. So why on earth am I going to go find that negative 2? The negative 2 that's illegal to even occur. And why am I not drawing a hole, but I'm drawing a vertical asymptote right away?
It's gonna be like in between the asymptote.
There's stuff on either side, but how do I know it's an asymptote? Why couldn't it be a hole?
Because it can't be factored.
Can't be factored. You see it? What's my problem here? Well, x isn't allowed to equal negative 2. Yay, let's get rid of them! Unless you kill a kitten and say, I don't know, I don't like you, or you, or you, or you, or you. 7! No. Any of you that would want to cross out anything are doing basically something as mathematically ridiculous. I understand why there's a mistake. That's why there's a kitten thing on my board, on my wall. But this numerator, this denominator, do they match?
No.
Can I factor him? No, it's not even a square. I'm stuck. They're linear pairs is what we call them. So since I'm stuck, guess what? The discontinuity cannot be removed. Can't be factored out or away. If it can't be factored out or away, I'm stuck with them, and if I'm stuck with them, that discontinuity is a vertical asymptote. Now, what does the graph look like? Oh, that's the bummer. Well, there's nothing left after dividing because it's not going to work dividing anyway.
Don't you just divide or multiply the conjugate at the bottom?
You could start playing with stuff, but the problem is then we're bringing in more and more factors, making it bigger and bigger instead of doing the same way.
So you just leave it like that?
Yeah, nothing else we could do. So I wonder if right now we can't tell what it looks we have this page? Well, we have this page because we just talked about if there's a whole, not everything is awesome, but at least everything is kind of nice because we can divide and get a simpler form that maybe we know the graph of. But for vertical asymptotes, we just talked about how we're stuck. So we don't know what it looks like off top of our heads, but that doesn't mean that we can't learn something about what it looks like. That was to have a vertical asymptote somewhere in space. There are 3 different ways of graphing it closer and closer and closer to a vertical asymptote. Now, it's not the only types of graphs that can, but in general, as you get closer and closer and closer to a VA, you have to skim it somehow, and to skim it, well, you're either going down or you're going up, or you're doing a little bit of both. Or vice versa, you could also switch it. Either you're going down together, up together, or a little bit of both together. Somehow, if you need to skim a vertical asymptote, that's how all vertical asymptotes work. You're either going down or you're going up. Wait, going. Oh, mathematically, there's a snazzy term for going. The function's going up, increasing. There's a way of writing that. The function's going down, decreasing. There's a way of writing that. Do you guys remember? The word is approach. What's the symbol? Arrow. Nice. So f of x is either going to be approaching positive infinity, going up, or negative infinity, going down. Now remember, that's our snazzy f of x. But tomorrow we're going to have to figure out how on earth do we figure that out without a calculator. There you go. Bye guys. Happy Tuesday, happy Thursday, happy Mr. HCS's Tonight Day. Come see Justin Liu in action and John Yoon. Whoa!